Okay, great. So I'll just kind of I think everybody was on the right track. The answer to this one then, since everybody thinks they had it, and I'm pretty sure you guys all said the right number, was that you should get Q dot equal to negative 61.3 kilowatts. Is there anyone who got something else other than that? Awesome. So if you got that same number, then, oh, hold on. Okay, so Brian had 55.1. Let's think here. Do you have your problem right there? We can kind of run through some numbers and see where the issue was. What did you get for let's see here. So what did you get for let's see, for H1, that should have been, so that on the intake, the enthalpy should have been 3177.2. Yeah. Okay. H2, 2345.4. You have 2345. Okay. Yeah. Within, you're good to like 4 digits. So that should be good. What about the kinetic energy then? So to do the kinetic energy, you would have velocity 2 squared over 2 minus velocity 1 squared over 2 to get the difference here. And when you plug in meters per second, so if you use meters per second for velocity, that's going to mean that this thing comes out as joules per kilogram seconds. So what you need to do is, when you plug this in, you need to multiply by 1 over 1,000, and then that'll get you to kilojoules. Because because there are 1,000 joules in a kilojoule. Did you do that part, Brian? Well, if you divide by 1,000, you should get 1.2 kilojoules, right? That's what you're getting. All right. So then the last thing is the flow rate, m dot, was given as a stupid amount. They gave you 4,600 kilograms per hour. And so you need to multiply that. Basically, you need to do, think about that. 1 hour is 3,600 seconds. So you got to, so your m dot is 4,600 over 36. So it's 46 over 36. And if I type that in here, give me a second here. 46 divided by 36. And it gives me 1.228, let's call it. Did you use that? Yeah? Okay. All right. So then, and then did you account for and you had 1,000 kilowatts of work being provided. So, all right. So when I pull it all together, I should get Q dot should equal W dot plus M dot times H, let's see, it'd be H, H2 minus H1, the change in enthalpies, And then I also have the change in kinetic energy terms. That stuff. And when I plug in numbers here, I'm getting 1,000 plus 1.28 times. And if I subtract these two, you're going to get 831.8 plus 1.2. I think if you go through that, I think that comes out to be negative 61.3 kilowatts. So I don't know. It sounds like you had all the right numbers. So I don't have my calculator right here. Not very smart. But it could just be a typo, I guess. I don't know. All right. You had negative. Oh, you're right. Yes. Yes. Sorry. Awesome. Okay. Okay. All right. So the plan for today is to kind of go through the other devices, and then I'm going to do the same thing. I'm going to leave you with a problem to work on. It's a little bit more fun than this last one. We can kind of unwind what you should do for this one. And then I will leave you to find the numbers, and then we'll check in. And then on Friday, then we should be able to start building thermodynamic systems. So I'm going to be, there won't be an assignment due this Friday. I'm going to have kind of a long one due next Friday. It'll be on power cycles, refrigeration cycles, using all these different devices and components to build, a refrigerator, or plan, at least not build, to plan a refrigerator or power plant. So there won't be an assignment due this Friday. There will be one due next Friday. I'm going to try to get that posted today, because after today, you will have all the kind of standard assumptions ready, and you just kind of have to start working on it. And it will take a while to do. So please don't put it off. All right. Okay. So let's start. Can everyone, I should have asked this, can everyone see the notes that I've got going here with the images? Can you guys see those? Can you see the reciprocating compressor image? Nobody's saying. Yeah, Gabe can. All right, good. Very good. Okay, so compressors. So we're going to go through compressors, boilers, heat exchangers, throttles. I think that's, okay. I think basically everything else. So let's start with compressors and pumps. In the image here is a reciprocating compressor. So you have a wheel that will spin. And as this spins, well, actually, for those of you guys who did programming with me, you'll remember this. This is basically, remember the piston assembly that I had you guys figure out how to animate on the using Mathematica? There you go. So it's as this spins around, the piston goes up and down, or in this case, left, right, left, right, left, right, left, right. And what you do is you have a set of valves such that when the piston is, I guess when the piston is going to the right, then you intake air, and when the piston is going to the left, then what will happen is this valve will shut, and this one will open. So I should have said that here. This valve will be locked on the intake. So the idea is it's kind of like a ratcheting mechanism. It only allows the flow to go one way, and you can adjust the valves and things so that it won't open, say, until you reach desired pressure. So in that way, you can take a gas. If you have a compressor, compressors use gas typically, and so you would have gas coming in at one pressure, and then it gets squeezed, and as it squeezes, it's not allowed to backflow, and you might arrange it so that this check valve doesn't open until desired pressure is achieved. And so you've got a machine here where the intake is at one pressure and the outlet is at another pressure. And so so compressors do what you think they do. They increase the pressure of the gas typically. Okay. Who's kind of seen it or messed around with a device like this before? Has anybody ever pulled one apart? No, not really. Okay. All right. There are other kinds of designs. This is a reciprocating compressor. This is these are rotating compressors, so you would have an axle that spins, which turns a fan blade. If it's a compressor, it's spinning like a propeller that's going to squeeze the air, and what you're basically doing as a propeller blade spin, like in this one, they would force the air or the gas forward, but as it does so, it kind of has a nozzle, so it gets squeezed. You can have other ones where, they're just different ways to do it. For example, this one is kind of an interesting one. It goes in and you arrange it so as these things spin, none of the air doesn't actually go through the center. It gets squeezed and kind of trapped in little pockets that are created as these, I don't know what you call them, these elements spin, rotors or something. You can also have very similar sort of devices for pumps. If you want to have a liquid, use a pump typically, unless you have that typically liquids are for pumps are for liquids, and compressors are for gas or vapor. But anyway, so they both compressors and pumps achieve, from a physics side point of view, they achieve the same basic result in that they increase the pressure of the fluid. Okay, that's what they do. They are devices which increase pressure. All right. So the various, just like we had with a turbine or a nozzle and diffuser, there are various standard assumptions you can make. First of all, they cause, grammar's bad even for Indiana standards. All right. They cause changes in pressure. Typically, they're not so big that you incorporate potential energy changes. So you can ignore potential energy effects as usual. Usually, you can neglect the changes in kinetic energy. There would be some change in kinetic energy, but more or less, numerically, it comes out to be a small effect. So you would typically drop this unless the problem specifically gave you those numbers, and then you would use it, like in the example we did last class. So usually ignore potential energy, ignore kinetic energy. A lot of times we will ignore the heat. There is typically heat loss or heat exchange, but numerically it usually is a small percent kind of effect. So we drop it when we do kind of simple modeling, unless the problem explicitly says the heat is something, then you have to include it, of course. Okay, so if I use, oh, and the other thing is these devices, pumps and compressors, are squeezing the fluid. So that means they are doing work on the fluid, which in our sign convention means that the power, W dot, is going to be negative. The fluid isn't driving the pump is driving the fluid. So W dot is negative. Okay, so that's just a check. You do the math and it better come out that way. All right, so what I've done is I've just kind of taken our control volume equation for the energy equation, and I've applied all these standard assumptions. And again, because there's only one intake and one outlet, you kind of, there's only one M dot, and I just call it M dot. I don't label in and out. And so I've dropped the heat, I've dropped the kinetic and potential energy, and I've just rearranged it. And the only thing really that survives are the enthalpies and the power. Okay. Are there any questions? Do you see where I'm getting this? I don't want to go too fast on that. Is there anyone who doesn't understand where I'm getting this equation? I can run through it. Maybe I'll just quickly remind you from last class. Okay, when we had just a single input and output, the energy equation was Q dot over M dot minus W dot over M dot plus enthalpy, kinetic, and potential energies, inlet minus outlet. And then if we're going to ignore kinetic, ignore potential, these other terms go away. And then if we're dropping heat, then we're just left with the work. And I am afraid that I make a mistake. That I have a minus sign. Moment of panic. Oh, I got my minus sign right. So I'm good. Had a moment of panic that I dropped that minus sign. Okay. So that is the kind of a standard sort of modeling equation. So if they say it's a pump and they're not giving you any particular details, you can pretty much go straight to this equation. All right, no questions. Condensers and boilers. I guess I got my images backwards. So a condenser, it's like what we saw with the refrigeration unit, right? It's you arrange for the fluid to kind of zigzag through, and you let it come into contact with something that's going to be colder, typically, to extract heat out. And so maybe it enters as a vapor and it leaves as a liquid, typically, but you have to look at the numbers to check that out. Sometimes there's a fan, but not always. It could just be open to the air. So you'd be using, so the question is, are you using kind of free convection or forced convection to cool it off? A boiler, on the other hand, is it's kind of the opposite of that. Instead of putting it in contact with something colder, you have the fluid coming in. You have fire or something that's very warm, and then you allow the fluid to leave. Okay. So as far as the fluid flow that we care about, I don't really worry too much about the air in these cases. So there's one inlet and one outlet. Again, one inlet and one outlet for both of these devices. So they're pretty simple. If you kind of think about it, the pressure won't change very much along these devices. What sort of happens is, if you had a big difference in pressure, then the flow would sort of adjust. It would sort of speed up or slow down to kind of re-equilibrate. So the pressure, when you run things in steady state, then you can assume that the pressure is constant throughout a boiler or a condenser. So they're isobaric processes. So that's an assumption that isn't always spelled out in the problem, but you can. If you have a boiler or a condenser, the pressure will be constant. Again, ignore potential energy. Also, like some of the other devices, we can ignore kinetic energy it's not that it won't change, but the change is not significant, it turns out. So you can ignore that. These devices do not have a propeller or blade or fan spinning in the fluid flow. So a lot of times we just set W dot, the power, to 0. However, if you had driven, if you had forced convection, that fan would take power, and so you would have to account for that for getting your bookkeeping right. Maybe, it just depends. Maybe it's a small number and you don't care. But anyways, with the standard assumptions, we will drop the power, but you might have to go back and modify that for more realistic modeling of a system. And the whole point of these devices is that they cause heat exchange. So Q dot is not ever going to be 0 for a boiler. The whole point of a boiler is you're dumping heat into the fluid. The whole point of a condenser is you're extracting heat out of the fluid. So Q dot is not 0. So with these standard assumptions, we can go back to our energy equation for one intake and one outlet. And now there's no work term typically, but you do have a heat term, and so it comes with a plus sign. Incidentally, I should have said this, it's not only is the heat, well, for a boiler, the boiler gives the fluid heat, so we expect the heat to be here, positive for boiler and negative for condenser. That's right. I think I misspelled it earlier. Okay. All right. So positive heat for the boiler, negative for the condenser. Just think about what they're doing and what they're accomplishing. There you go. Other questions about that? All right. All right. In the chat window, let's make sure everybody's awake. You guys are not too vocal today. In the chat window, I want everyone to write down, without looking in your notes, you have to be honest. Without looking in your notes, write down the standard, or write down, let's see, for a nozzle and diffuser, what would the energy balance equation look like? Can you write that down in the chat window? So let's think about it. Nozzle and diffuser. Is there going to be work? Yeah, with the assumptions. Yeah, make the standard assumptions for a nozzle and a diffuser. What would the, yeah, no work because there's no fan blade or anything. Is potential energy significant? Oh, there you go. Yep, Brian's got it. Yeah, unless going down a well. Yeah, we're not going to do that. All right, so Brian wrote it there. Okay, so I'd only quibble, and you would say, Brian, you'd say equals 0. Right? Yeah, because it's steady state. When it's steady state, it's all that stuff equals 0. And we only do steady state. So it's always blah, blah, blah equals 0. Okay, so maybe there's heat. In fact, a lot of times with nozzles and diffusers, it depends on the stuff. There may not be much heat, actually. A lot of times you set the heat to 0, but maybe heat. Delta H, and you could have kinetic energy. Again, it may even be no change in kinetic energy. So if you have really small velocities and not much heat, then actually you just say that the enthalpy is constant across the nozzle and diffuser. But okay. All right. What about a turbine? With using standard assumptions, what would you write down for a turbine? Does it have work? Yes. Does it have heat? It's one of those, yeah, it's one of those, it might have heat, although the heat might be negligible sometimes. So, if you're doing really simple modeling, and it definitely, and then you have that, you don't typically have large changes of kinetic energy. Yeah. So you're typically, it's not that the kinetic energy doesn't change, it's just not as big as the other numbers. But if the problem gives you numbers, then maybe you have to do that. I should have said that. In the example we just did last class, I should have pointed out the kinetic energy, let me look at it. The kinetic energy was about a 1 part in 1,000 effect. So for a turbine. So, okay. Awesome. Oh, one thing, Alex, I know you're just typing it. The W dot comes with a minus sign. So it would be 0 equals Q dot over M dot minus W dot, these should be capitals.
Time for lunch.
I only feed him like 12 times a day. Jeez, it's like a hobbit or something. All right. Okay, yeah, so just watch that minus sign. How many thermal problems do you have to do for the sandwich? Well, if you cook it in steady state, no, that would be like thermochemistry. So you'd have to drive a chemical reaction. So sorry. Okay, and then we have the last two that we just did, which are very similar. You just go through, and the first thing, notice when I thought through what assumptions, I mean, you can try to memorize it, but I always get confused. So then I just think about, okay, is there heat? Yes or no? Is there work? Yes or no? Is velocity changing much? Yes or no? Is potential energy important? Yes or no? And then I just keep what survives. So for compressors and pumps, typically the heat is small. It might not be, but typically it is. They always do work. And so you have work and enthalpy. The kinetic energy stuff isn't going to be important. And then for condensers and boilers, it's kind of the same, only instead of work, you have heat. Everything else is about the same. Okay, everybody clear on that? All right. And then what about heat exchangers? So heat exchangers, morally speaking, is just like a boiler or a condenser, right? They're kind of a dummy passive device that just, you just arrange things to flow, a hot thing flow next to a cold thing or vice versa. Or mixing chambers, same kind of thing. What can differ though is with these devices, typically you're keeping track of not only say maybe the water line, but maybe you're also keeping, or the hot fluid, you're also keeping track of the cold fluid. And so the example I'm going to give you is a reheat cycle where you're imagining you're burning something and then you're trying to capture the hot gas and reuse that and recycle that to boil water or something. So so what happens is in this control volume, if you look at how the dotted lines are, you have it's everything here. And in this case, you have fluid flowing in, and like something like this, you're going to assume that there's no heat loss across the control volume. How is that possible? I just said that they're like a boiler or a condenser. What's happening here? Why would I say that there's no heat loss in this heat exchanger right here? Can someone tell me? Okay. Well, think about what's happening. There's heat exchanged between the fluids, right? But there's no significant heat lost into the air necessarily, unless the problem tells you that. So I would, if I was modeling this, I would say there's no heat to the outside volume. What I would intuitively want to think of as heat exchange actually is between the two fluids, and that's all internal stuff, right? So, and remember, the changes are just at the boundaries of the control volume, not inside. You don't worry about stuff that happens on the inside. So what actually is going to account for so what you're going to have is a change in enthalpy for the fluid in green here in this image, and you're going to have a different change in enthalpy for the fluid in the gray pipe here. And the fact that I have two different fluids, each with their own different changes in enthalpy, that is what is going to account for the heat exchange, right? So the heat transfer between the fluids isn't going to be a heat transfer for the control volume, because that would be stuff going into the outside environment. There's nothing for that. Instead, when those two pass energy back and forth, it manifests itself as just different enthalpy changes for them. The other complication for these is that now you don't just have one inlet and one exit, you have two inlets and two exits. And so that means that when you write down your energy equation, that you can't just call it M dot. You have to label M dot input 1, M dot input 2, exit 1, exit 2. Okay. So when I wrote down the so I should have also said that but you make basically the same assumptions you would make for a boiler or condenser. So in particular, constant pressure. So you would assume in this one that the pressure is constant along the gray line or the green line. It doesn't have to be the same between them. The pressure along the gray pipe doesn't have to be the same as the pressure on the green pipe, but you would assume along each separate pipe it is constant. Now, in a mixing chamber, that wouldn't be a good assumption. You could have high pressure you have different pressures at all three in principle there. But when you've got these isolated streams, you would want to keep the pressure constant along each one of them. There's one other one here, this cross flow heat exchanger. That one, if you look at the way they drew the dotted lines for the control volume, that one actually would have heat going in and out and stuff. So you'd have to keep track of it. All right. So I should have written one more equation here. I forgot my mass balance equation. So I should have also said M dot M, sorry, I1 sorry, I'm just writing these all in LaTeX, and it just is kind of a pain. E2. Sorry.
From your calendar, Science Everson starts each.
It's taking a second to compile. Okay. So I should also have this equation. Oh, plus.
From your calendar, sign starts in 2 minutes.
The mass flow rate should balance. So you add up all the inputs, that should equal all the outputs. Okay, so that's another equation. This one's kind of a trivial equation when you just have one input and one output, but for heat exchangers, you have multiple ones, and so you have to add them all up. Are there questions on that? All right, our last device is a throttling valve. It's particularly simple. There's one inlet, one outlet. So m dot is constant throughout. Ignore potential energy, ignore kinetic energy. You run these things at low velocities. If you tried to have high velocity, it would blow out. The pressure would be such that the device would fail. It would crack. So you run it at low speeds, so therefore you can always ignore the kinetic energy. There's no propeller or anything, so there's no power delivered. Usually, you can assume that the heat loss is small because these are typically not large devices. And you can imagine that you shrink wrap it and insulate it and stuff. So you usually ignore the heat. So if there's no heat, there's no power, there's no kinetic energy, there's no potential energy. The only thing left is enthalpy. And all I get is the enthalpy of the input is equal to the enthalpy of the output. So they are isenthalpic. That's a good, fun word. Isenthalpic. Isenthalpic. Constant enthalpy. All right. So they're pretty simple things to work with from a math point of view. And then we get to our practice problem. All right. So what I'm going to have you guys do, let's see. So I'm going to split you guys into
Sean,
yep.
For like 1 second. Sorry.
What's that?
Can you go back up to the throttle so I can
oh yeah,
just take a picture real?
Yeah, sure. I'm going to post all these I'm posting these on Blackboard too,
Oh, I was writing it all down.
Well, now it's in your brain. So I'm just going to export these notes to PDF. The ones from last class are there, and I'm just going to update it to these other devices there. Okay. All right. So I'm going to have you guys split for about 10 minutes into 2 groups, and then I'll pull you back and we'll kind of talk through this. Don't worry about getting numbers. What I want you to do is to try to plan what you're going to do for this one. Okay. So, but maybe take a picture of the actual problem though. That would probably help because it's got a lot of words. All right. So I'll read it to you. There's an industrial process discharges. So this is a heat waste recovery system. So the idea is you've got this hot exhaust, and so you're like, well, okay, maybe I can use that, and I've got some other water that I want boiled. So maybe I can use the exhaust that was just dumping into the air to heat up the water. And so the question is, the real question is, how much money can you save by doing this? That's really the question, but all right. You're told that there's some process which discharges 2 times 10 to the 5 feet cubed per minute. So that would be the volume flow rate, V dot, right? Feet cubed per minute of gaseous combustion smoke. And when it leaves, it's at 400 degrees Fahrenheit and 1 atmosphere. 1 atmosphere would be 14.7 psi, and you have to convert that to foot-pounds and then go from foot-pounds to BTUs. So anyways, we're going to have lots of unit conversions here. Okay. Oh, they will give you a picture. I'll draw the picture. You know, my artwork's so good anyway. Okay, so I will draw the picture here for you to look at. So the gas has that. So let me do that now. So the idea is this. You've got your control volume is going to be inside this. So here's the deal. We're going to have like a heat exchanger. So we're going to have gas in, and this is going to be state 1. So P1 is 1 atmosphere. And the temperature at state 1 is going to be 400 degrees Fahrenheit. And they give me the volume flow rate at state 1 is 2 times 10 to the 5 feet cubed per minute. Somebody. James, did you miss science? Okay, so we have that. And then, so this is going to be fluid that goes in, or sorry, it's going to be gas. It's going to be, smoke. And they say model it as air, treat it as air, treat it as an ideal gas. And then we're going to have water, which is going to come in as liquid. So we're going to call it state 1. At state 2 is when the gas leaves. State 1. Water is going to enter at state 3 and leave here at state 4. And then it's going to run into a turbine generator and then leave at another state. I'll call it state 5. Okay, so the smoke flows here, the water is going to flow here, and I'm just going to kind of fill in the numbers here. So when the combustion exits the steam generator at 260 Fahrenheit, so the smoke leaves at 260 Fahrenheit as it leaves. And it's 1 atmosphere because it's isobaric along a heat exchanger. The entering water enters at a pressure at state 3 here, which is given as 40 psi. And the temperature at state 3 is given as 102 Fahrenheit. So the water enters here at 40 psi, and it's slightly over 100. But because the pressure is really high, it still is liquid. So it's going to enter as liquid. You're just going to have heat exchange between the 2 pipes, and it's going to leave as, let's see, how does it leave? It leaves, it's going to leave as a vapor. We don't know anything about the middle state, but we know when it leaves the turbine, here, we know that the pressure at state 5 is, the pressure at state 5 is 1 psi. And we know the quality at 5 is 93, so 0.93. The other number they give me is the mass flow rate here, m dot 3 equals 275 pounds per minute. Whew. Okay. I think I've got all the numbers labeled. Yes. Okay. They want us to determine the power of the turbine. So figure out the power of the turbine and determine the temperature as the water goes into the turbine. So the temperature at state 4. So find, so we want W dot for the turbine. We want the temperature at state 4, the temperature right here. And we want to know about money. Is this a good idea? Do we save money doing this? All right. So that took way longer than I thought I think we're not going to draw the picture. So we're not going to have time to break out into groups. Okay. Let's talk through how you can analyze this, because this is what I want you to do for Friday. Not knowing what to do. I mean, I have the book here. If I was looking at this, what I would do is I would start with a place that I have lots of information and just kind of feel my way around the different fluid flows. So in this case, I would actually start at the heat exchanger. And I would use that information to figure out what was happening here as it left the heat exchanger. And then that would tell me what happens, what the change in the state of the fluid is across the turbine, and then I could use that to get the power. So my plan, which is a little different than what the book does, it doesn't matter, they all comes out the same, is I would type it here. If this was me, start with heat exchanger, to determine the state 4 and then get all the numbers I might need. And then work on the turbine. Okay, so that would be the strategy I would take. So let's see how that would play out. So to do that, from the heat exchanger, okay, what are the assumptions I can make? Somebody call them out. What do I know about the heat exchanger? What assumptions could I make for a heat exchanger?
No potential energy?
No potential energy. Is there going to be kinetic energy?
No.
Nope. That's one thing. Is there going to be any heat? I know it's a heat exchanger, but is there any heat lost into the room in this device? Also,
No.
how do you know that? Well, one is it's a standard assumption, and two, they didn't give me any numbers, so there's no way I could even estimate it. But so the fluids pass energy between them, but that's all inside the control volume. So you don't have to worry about heat radiating into the room. So it's just like this equation here. Okay, I'll rewrite it in a minute, but it's just like that equation. And oh, you have to be careful with the control volume, with the mass flow rate equation, even think about it, because the flow rates can't mix, right? The water here doesn't ever mix with the smoke. So that actually means that m dot at state 3 is going to be the same as m dot at state 4. Similarly, I know that m dot at state 1 is m dot at state 2 because they don't mix. So none of the masses aren't going to change. So let's write down assumptions I can make for this. I can say m dot 1 equals m dot 2. I can assume m dot 3 equals m dot 4. I can assume w dot equals 0, q dot equals 0. What else can I assume about boilers, condensers, and heat exchangers? What's another assumption I can make about boilers, exchangers, heat exchangers, and condensers?
Is it work is 0?
That's true, but I've already said that w dot 0 here. There's another one.
Pressure is constant.
Constant pressure. Yeah. So I can assume that the pressure at 4 is the same as the pressure at 3. Okay, remember the goal is to figure out the numbers for state 4. Now I know one number for state 4. That's 1. I need 2, but that's 1. The other number is going to come from the energy equation. This top one right here. Okay, because I will work out m dot for the inputs and the outputs, right? And then I will use the energy equation. So I can, okay, so I have that. The other thing that the problem tells you, which I said very quickly, but I'll reiterate it here. It says, blah, blah, blah. The combustion, the smoke, can be modeled as air in an ideal gas. And so that means we model smoke as air ideal gas. So that means we can look up numbers for state 1 and 2 from tables. There's an ideal gas table of enthalpies and things for air. So for states 1 and 2, you can just look up the numbers from the tables. All right. So what do we want to find? Right, so we're going to need, well, what are the list of numbers to get from the table? We want to find H1, and you'll also have to figure out M dot 1 Then you have to look up H2 from the table. M dot 2 is the same as that, as M dot 1. We'll need to look up H3 from the water tables for water. And then I'm sorry, so we need to calculate M dot 1. That's a calculation. Basically, but to do that, you're going to need, when you make, you might need to use ideal gas law. Think about it. You might need to do that to get M dot 1. And then from the energy equation, you can find H4 from the energy equation. All right. Let me pause there. Other question? Do you guys understand my kind of my thought process on how I'm going through this one? Nobody's. So I'll tell you what, give me a thumbs up if you understand the assumptions I made, where they all came from. Okay.
To find M dot 3 and 4.
M dot 3 was given, and because they don't mix, M dot 4 has to be the same.
Gotcha.
Oh, and on top of all this, actually before you get H3, unit conversions. Okay, there's going to be a bunch of unit conversions you'll need to do to get that. You need to get, so you want in BTUs per LBM. All right, so when you do, well, you just got to get the units right. So, okay, so you got to watch the units there. Okay, so let's imagine you get through that far and you find the enthalpy at state 4. And when you, in the process of doing that, you can get, and then from that, after you get that, you can get the temperature. Okay, so that'll come out as you do it. Let's talk about the power of the turbine. What are the assumptions for a turbine? What assumptions are you going to make here? Did they give us any way to think about heat? Did they give us any knowledge or any way to even estimate that?
No.
No. So we're going to just assume that heat is small. We don't have a way to even estimate it if we wanted to. Okay. Is there work for a turbine? There's a propeller there, so yeah. Well, and the whole point of this is to, well, actually, if you read the problem, they want you to boil the water to turn a turbine. So you're actually trying to produce electrical energy. So we're wanting to produce power. So there will be work. And then there's no kinetic energy that's significant or potential energy that's significant. So we can say KE equals 0. Well, not 0, but ignore. Let's put it that way. KE ignore PE ignore those things. And so then we're left with a really simple equation. We're going to get that 0 equals W dot divided by M dot. Oh, there's a minus sign there. Plus the enthalpy of the inlet. Which of the, on the water line, which is the inlet for the turbine? Which number?
4.
4. Yep. So it's going to be H4 minus H5. Okay. Can we find H5? Definitely, because they give us 2 numbers. So let's go back and edit this thing. Find H5 from the table. And then find power from that. Okay. So the turbine part's going to be easier than the heat exchanger. All right. Give me a thumbs up if you feel like you understand these assumptions and how to proceed to find the power. That's fine. Brian, you okay? Yeah, he's okay. All right. Okay, I'm going to post this just as it is to Blackboard. So I basically have given you a roadmap through the problem. So just work through it, and then we'll talk on Friday. Okay? All right. I'm going to let you go then.
Sean, can I talk to you after the
Yes.
class?
Yes. Yes. Let me stop recording and we can. All right. So.
Hey, Sean, I had a question for you too, but Sapan can go first.
Oh, okay.